Hi. In our previous experiments and what we did till now, we assumed that the light ray was going from air to water, that is, from an optically rarer medium to an optically denser medium. But in this video, we will see what will happen when our light ray goes from an optically denser medium to a rarer medium. So some results are obvious, it will bend away from the normal, but a very special case arises. How does it happen and what happens? Well, we'll see. So here's the apparatus. This is the jar. You might remember it from our previous experiments. And I've got this laser. Okay. Now let me switch on off the lights and incident this light from water to air. Okay, you see clearly it bends away from the normal. So if you draw the normal, which is nothing but a line perpendicular to the plane of water, as you can clearly see, it is bending away from the normal. Now what will happen if I increase angle of refraction? I'm increasing it. Okay, imagine a normal at that point and you will see it will gradually increase. You see what happens? Light is not going from water to air, it's reflecting back into the water, and this phenomena is known as total internal reflection. Yeah, so totally the all of the light is getting reflected back in the same medium. There are no mirrors here clearly. And this happens when light goes from a optically denser medium to a optically rarer medium, that is air in this case. Now a very special angle comes into play when an angle of refraction becomes 90 degree. That we shall see now. So here's what happened. Let us say this is our interface. So I am drawing the general cases, and here's our source. Let us call this source S, laser in this case, and it emits light. Okay, and let me draw the normal. So this is the normal. Okay, and we make this dotted. Now what we noticed is that as our angle of refraction increased, angle of incidence, this one, so as this angle increased, our angle of refraction, that is this one, that's it, it will bend away from the normal. Our angle of refraction, let me do this with a black pen, also increased. Now my question to you is, can we go on forever? Think about it. Let us say this is mu1, first refractive index. Now this is, and let us call this mu2. Now as our I increases, our angle of incidence increases, our angle of refraction will also increase. Okay. Now after a point, this line will effectively go down, keep coming down, and at a very particular angle, it will become perpendicular to the normal. So how will it look? Let me draw the diagram. Let us say this is the angle which we are talking about. So that's how light is incident, and it becomes 90 degree. Okay, so this angle is 90 degree. Now that angle right at which the refracted ray becomes perpendicular to the normal is known as the critical angle. So this angle is known as the critical angle and is generally represented as theta c. So critical for c and theta is a general notation for angle. Now what will happen if we increase the angle even more? What happens is, just like we saw, that's how light rays will get incident, and let us call this angle the really big one, theta naught. It's just a random angle. Light will bend into the same medium, and it will obey all the laws of reflection. So angle of incidence will become angle of reflection. So this angle is theta naught, this angle will also become theta naught. Now let us find this angle, shall we? So what does Snell's law tell us? Snell's law tells us, okay, we take sin I by sin r. So sin I, this angle, and we divide it by sin r. This will be ratio of second refractive index, mu2 by mu1. This is what Snell's law tells us. Now our angle of refraction, this one, is 90 degrees. Clearly, yeah, you can see this is 90 degrees. So what is sine of 90 degrees? Sine of 90 degrees is nothing but 1. So and the particular angle at which the refracted ray becomes perpendicular to the normal is known as critical angle, hence the name. So theta c, let me write this down as sine theta c is equal to mu2 divided by mu1. This is how you solve for critical angle. And of course then sine will go there, and as I discussed in my trigonometry videos, theta c will be nothing but sine inverse mu2 by mu1. So those who have encountered sine inverse for the first time, sine inverse is nothing but tells you that, okay, give me a numerical value and I will give you an angle. That's what sine inverse tells us. Now these two are the general cases for evaluation of critical angle, but in many questions and in many situations, this medium is air. So mu2, it's going from a denser medium. It might be anything, it might be glass, it might be water, into air. And as I discussed, the refractive index of air is approximately mu of air is 1.0003, and we say that, okay, it's as good as 1. So we approximate the refractive index, the absolute refractive index of air as 1. So we can say in most cases that theta c, the critical angle, is sine inverse, okay, and mu2 becomes 1. Yeah, so this becomes mu2 in this case, 1 by mu1. There is no need of writing 1 and 2 here. The refractive index of this medium, the denser medium. So for many cases, this might be considered as the equation for critical angle. Now again, the applications of this is what we see in a rainbow. So in a rainbow, we can discuss rainbows in another video, but what happens is in rainbows, water droplets, so this is a droplet of water, and this is just an introduction. The actually what's happening is slightly, we can do this in another video in a more detailed manner. What happens is light comes, it bends a little, of course, and it gets totally internal reflected. Okay, it becomes totally internal refracted, and then it bends at the surface. So that's a very basic introduction. This is water dominant to how rainbows are and how we see rainbows. So guys, that's it for now. That's it for today. And I really hope you liked this video and learned something new about the critical angle. So thanks for watching.